The first application of integration we're going to talk about in this course is computing volumes of objects. And the way we're going to talk about computing volumes of objects is really by revolving a function about a particular axis to trace out a three-dimensional object for us. So for example, if we just take, say, a line, so we have the X and Y axes, and we just have, let's say, a shape, just a line segment that goes from some specified Y value at X equals 0, and then crosses the X axis there. So this is our function Y equals f of X. And when we talk about making a shape, we're talking about revolving that function around a particular axis. In this case, we'll think about revolving around X. So we're really thinking about then revolving the shape around our X axis. And when we do that, say, for example, we take this point, what we're going to see happen is when we revolve this in a very much three-dimensional way, revolving is sort of a circular motion. We're just going to take this point and it's going to trace out a circle basically. And if we take any other point along that object and kind of revolve it around the x-axis, it's going to also trace out a circle. So if we look at what object this actually makes for us, for example, revolving this line around the x-axis, this makes a cone. Basically looking at our function just by itself, taking away our axes. So what we're going to talk about is how can we do this revolution of a function around a particular axis and compute that function's or that object's volume. Now, this cone might seem a little simplistic because you may remember the volume of a cone. And in fact, we're going to go through that derivation in class. But you might imagine we could have a more complicated function. So for example, what if we had a function that, say, did a few more squiggles, and we revolve that around, say, the x-axis. So when we go ahead and revolve this function around the x-axis, it's going to trace out a more complicated shape, one that I'm willing to bet you've never thought about how to compute its volume of revolution before. So if we try to draw this, which will probably be a bit comical, by itself, without sort of our axes grids, this shape would trace out something that looks like the following. Where basically the dotted lines tell us that that's actually inside of the object. So we're wondering what would be like the volume of shapes like this. And we're going to talk about these types of things in class today. And we'll see that the ideas that are going to help us out is remembering what the area of a circle is, and then taking that idea of what the area of a circle is and multiplying it by a very, very small thin thickness to give the volume of one little slice, and then adding up a whole bunch of slices together.